All right. So in today's lesson, we're going to continue with this, idea of choosing between two viewpoints of the world. And we're going to try and formalize some of the intuitive ideas we presented way back in last Wednesday's lecture. But we're also going to do a fair bit of review since it's been a while since our last lecture. Okay, so for context, what we've been trying to do in this last few lectures is choose between two viewpoints or models of how the world works based off of data we have access to in a sample that we have collected. Okay, so one example that we've looked at repeatedly is, I found this coin on the ground. Is it a fair coin or not? And so the two viewpoints are, the coin is fair and the coin is unfair. Okay, or that's one pair of viewpoints I could come up with. But what we're seeing is that it's not always clear whether the data in our sample is consistent with one viewpoint or the other. Right? It's not clear which viewpoint to choose based off of the data that we've collected. And also, right, we're making all of these decisions based off of the data that we have collected. So for instance, the number of heads and tails that we have observed. But it's possible that the data that we have collected just happened to turn out really unlucky and looks one way, when in reality, the underlying truth in nature is the other way. Right? And so we need to come up with a framework that accounts for all of this and allows us to systematically choose between one of two viewpoints. Okay? Now, we've been using the term viewpoint or view, but a more formal term for a view is a hypothesis. Okay? Hypothesis with an is at the end is singular. Hypotheses are plural. Okay? And so what we are really doing is testing which of two hypotheses are better supported by the observed data. Like, for instance, I saw a coin on the ground, I flipped it 400 times, I saw 206 heads and 194 tails. Which hypothesis is better supported by that data? The coin is fair or the coin is unfair? And what we are doing is, developing a framework to answer that question. Okay? Now, these hypothesis tests, which again are just choosing between one of two hypotheses, they don't guarantee that either hypothesis is correct. They sort of just say, the data seems like it better supports this hypothesis. But we truly don't know how the world works, right? We're not, I don't want to say God, but we're not God, right? All we have access to is data in a sample, so we can't guarantee which of the two hypotheses are correct. We can just look at which one seems more likely given our data. Okay? Now in this class, the way that we will conduct our hypothesis tests involves simulating data under one of the hypotheses. Okay? And that's important because the hypothesis that we simulate data under is called the null hypothesis. Okay, so specifically, the null hypothesis is a well-defined probability model about how data was generated. Okay, and it's important that we are able to simulate data under the assumption that the null hypothesis is true. And so instead of saying, under the assumption that the null hypothesis is true, repeatedly, we will just say, under the null hypothesis, or under the null. Okay, so when you hear under the null, later on in lecture and in your assignments, all it means is under the assumption that the null hypothesis is true. So you'll have two viewpoints. The null hypothesis is the one that you simulate data according to. The alternative hypothesis is just the other hypothesis, or the other viewpoint. Do we agree? So now we're just giving formal names to the two viewpoints or two hypotheses we've been looking at. Questions so far? Okay, so here's something I want you to discuss for 30 seconds. Let's consider the pair of hypotheses. This coin is fair, and this coin is unfair. Which of these two is the null hypothesis? Or could either of them be the null hypothesis? Discuss for 30 seconds and enter in an answer at cc.dsc10.com. Go for it. c.dsc10.com. And again, feel free to grab candy. Okay. So it seems like the most common answer was C. Either could be the null hypothesis. Okay? And it turns out that the answer is actually A. It's the coin is fair. Okay? Don't get that happy. But and here's why. We've already run simulations under the assumption that a coin is fair. Right? Under the assumption a coin is fair, we can use np.random.multinomial, right, which is how we sample from a categorical distribution. And here that distribution is just 50-50. Right? Each coin we flip is equally likely to be heads or tails. Do we agree? All right, so assuming a coin is fair, we can simulate data. But assuming a coin is unfair, that could mean so many different things. Right? Is it unfair 60-40 heads? Is it unfair 90-10 heads? Right? If a coin is unfair, it could really mean anything. Right? And there's no way to simulate data under the assumption a coin is not fair in general. Do we kind of see the issue with that? Right? If the coin is fair, that means one very specific thing. It flips heads with probability 50%. If it's unfair, it kind of means that it could mean anything. Right? And so here, if we want to simulate data, the null hypothesis must be the coin is fair. Does that kind of make sense? Okay, good. So another idea we introduced in our last lecture was that of a test statistic. Right? And a test statistic is the number that we write down every single time we run one iteration of a simulation. Right? So some of the test statistics we saw in Wednesday's lecture was, for instance, the number of black men in a simulated jury panel of size 100. That was a test statistic. We also looked at the absolute difference in proportion of purple flowers and 0.75, which was specified by a model. Does that kind of sound familiar? Right? So these were all numbers that we wrote down each time we ran a simulation. And so the purpose of a test statistic is to give us information that we will use when trying to determine which hypothesis to side with. Okay? And so what we will do, and I'll get into this in a bit more detail in just a second, is we will simulate data under the null hypothesis, and in each simulation, we will compute a test statistic. So if we do 10,000 repetitions, we will have 10,000 test statistics, and that will give us a distribution. What we need to do is see where the observed value of that test statistic lies in that distribution. And that observed value is just called the observed statistic. So for instance, in real life, if I flipped a coin 400 times and saw 206 heads, and my test statistic was number of heads, my observed statistic is 206. Now in my simulations, I would have other values of test statistics, right? In one of my simulations, I might see 190 heads. In another, I might see 209 heads, right? So my actually simulated test statistics will vary, and that's why there will be a distribution. But my observed statistic, that's just one value. That corresponds to what I actually saw in real life. Okay? And one of the guiding principles we introduced last time was that we want to choose test statistics where large values point to one hypothesis and small values point to the other. Okay, it doesn't matter if large is null and small is alternative, or large is alternative and small is null. It doesn't matter which one is which. But we want our test statistic to be such that if it's big, it points to one hypothesis, and if it's small, it points to the other. In other words, we're going to sort of avoid test statistics where we have to look at the middle of the distribution or two tails of the distribution to get an answer. So if you've heard of a two-tailed test before, totally fine if you haven't. We will not be looking at those in this course. Okay? We design our test statistics so that we only need to look in one tail end of our histogram. Does that sound okay? All right. So here's another concept check. Let me delete my responses here. Let's again consider the pair of hypotheses. The coin is fair, or this coin is fair, and this coin is unfair. Which test statistics could we use to test this pair of hypotheses, given the framework I introduced on the previous slide, which is big values point to one hypothesis and small values point to the other? Which of these test statistics could we use? I'll give you another minute or so to discuss. Please enter an answer at cc.dsc10.com. Go for it. Grab candy. Okay. So kind of similar to the first question, the most common answer was more than one of the above. And kind of similar to that point, I'm going to say again that you're wrong. But let's look at each option here. First, the number of heads in 400 flips. If this number is big, like 300, that would imply that the coin is unfair. Do we agree? If that number is really big, that seems like the coin is biased towards heads. If that number is really small, that also kind of implies that the coin is biased, but just in the other direction, right? Biased towards tails. So this test statistic has this issue where big values and small values both point towards the alternative hypothesis, right? And it's values in the middle, close to 200, that point towards the null. Do we agree? Right, and so this has that undesirable property, right? We want to just say big values point to one hypothesis, small point to the other. And so we can't use option A. Do we agree? Do we agree with why we can't use A here? Okay. Now similarly, we also can't use option C. Right? Option C is very similar to option A. Right? Option C just takes the proportion of tails in 400 flips, so that might be like 0.6 or 0.4 or something like that, and from it subtracts 0.5. Right? So if this number is really big, it means the coin is biased towards tails, and if it's really small, it means the coin is biased towards heads. But again, we have that same issue where we have to look at big values of the test statistic and small values for evidence for the alternative hypothesis. And when this value is close to 0, well, then that's evidence for the null hypothesis. So do we agree why C has the same issue as A? Right? It's kind of the same thing, just one's divided by 400. Now B then is the correct answer here, because you'll notice it involves an absolute value. Right? So this is taking the absolute value of the difference in proportions of heads and tails. So if this number is small, it means the proportion of heads and tails were really close to one another, meaning that they're both close to 0.5. And if this number is big, it means that the number of heads and the number of tails were far apart from one another, meaning that the coin is biased in some direction. Okay, so if test statistic B is big, it means that that's evidence that the coin is unfair. If it's small, it's evidence that the coin is fair. So only test statistic B has that nice property that we like. Do we agree? Okay, questions with this idea, because it's an important one. Yeah?
The reason why A and C are wrong is because the high value shows that the coin is unfair, and the low value also shows that the coin is unfair.
Correct.
So just like for head and tails.
Yes.
And for B, high shows that it's fair, but then low shows that it's unfair.
is the opposite. It's high shows that it's unfair because it means that the proportions were different than 50-50. Low shows that it's fair. And we want test statistics where, say, high points to one hypothesis, low points to the other. A and C, high and low both pointed to the same hypothesis. It was medium or middle values that pointed to the other. And that gets annoying in the context of doing calculations for your tests. Does that kind of make sense? Yeah. Yeah. Not quite. So the null hypothesis is whichever one you simulate data according to. And in this distribution that I've been saying, okay, we look at one end of it or we look at the other, those are all distributions of test statistics under the null hypothesis. So we still can't simulate data under the assumption that the coin is unfair, right? Because how unfair would it be? Yeah, we're still simulating data under the null, and that's always going to remain true. Okay, so let's put this all together now, right? We simulate our test statistics under the assumption that the null hypothesis is true. So we might run, say, 10,000 experiments. Each one of those experiments will give us one test statistic. So we might get 10,000 test statistics. And those 10,000 test statistics constitute the empirical distribution of the test statistic, right? It's a distribution because it shows us all of the possible values of the statistic, as well as how likely they are to occur. So we'll see in our 10,000 simulations, for instance, what number of heads we saw often, what number of heads we didn't see as often, and so on and so forth. Okay? An important point to draw here is that all of these probabilities that we compute in today's lecture, they're all approximate because we're doing them all based off of simulations. Right? They're not exact. If you want exact probabilities, you'd have to do the math by hand. But as we're seeing, we will get essentially the same results, even though they might be off by 0.25% or something like that. Okay? Then what we need to do is take this empirical distribution of our test statistic, which will be that red histogram that we've been drawing, and see where our observed test statistic lies in that distribution, and use that positioning to make a determination on which hypothesis the observed data better supports. Okay? And so let's draw a picture here. Notice all I'm doing here is I'm simulating data under the assumption that I have a fair coin, or under the assumption that the null hypothesis is true. So 10,000 times, I flipped this coin 400 times, and each time I computed my test statistic, which is option B from the most recent question. Right? It's the absolute difference in proportion of heads minus tails. Okay, so this is proportion of heads, this is proportion of tails. There's the difference, and it's an absolute because I'm calling the absolute value function. Okay? And so what this is saying is, if I have a fair coin and flip it 400 times, here are the test statistics I would expect to see. So, my observed coin that I flipped 400 times, its observed statistic should come from somewhere in this distribution. And so maybe it'll appear here, maybe it'll appear here, maybe it'll appear here. And the question is, at what point in this distribution will we say that it's unlikely that the observed test statistic came from this distribution? Right? How do we conclude whether or not our observation is consistent with the null or the alternative? Right? How do we actually come to a conclusion here? And that's the question that we are going to address in the remainder of the lecture. Okay, questions so far? So again, this red histogram represents test statistics under the assumption the null hypothesis is true. So my observation, that has just one statistic, the observed statistic, it's going to lie somewhere here. If it's way out here, we'll say, hey, it doesn't look like that statistic came from this distribution. If it's somewhere in here, we'll say, hey, it does kind of look like that observed statistic came from this distribution. If it's somewhere in the middle, though, then it's not really clear, and we're going to make precise how we make these decisions. Okay, and so the example we're going to look at today involves the midterm scores from this past Friday. This is about as new as the data could get. Okay? Don't scroll ahead in the lecture if you haven't already. Okay? It'll be important. So this quarter, there are 4 sections of DSC 10, A, B, C, and D. Our section, if you don't remember, is C. Each student, as you know, is in exactly one section, and it turns out that one of the 4 sections had a much lower midterm average score than the others. Not going to tell you which one yet. We'll see. Okay? So let's look at the data. So this is real data. All we did was add or subtract randomly 0.5% from everyone's grade, just so that it's not your grades exactly, but the averages are still preserved. Okay, so for more or less, these are the grades of everyone in the course. Okay, so my data set has 2 columns, the section and the score. And so first I can look at the distribution of all scores, and notice this looks almost exactly like the one I posted on EdSTEM. Right, this is the distribution of all scores. Scores range from, say, 10 to around 77. You're welcome for that stimulus package of 7 points. But anyways, what we want to do is figure out what the average score of each section was. Okay? First, we can figure out how many students were in each section by grouping by section and using .count. So this will tell us the number of students per section. And if we want to find the average score per section, we can use .mean. And this is the real Halloween surprise here. It is our section. Okay? And this is my reaction when I discovered that. But yeah, okay, it was our section. Okay, keep that fact aside. So, with that in mind, let's suppose we randomly took all 393 students, which is the number of students who took the exam, into one of 4 sections randomly. Okay, so let's just presume that who's teaching the section and what section you're in make no difference. All right, we would take all 393 students across all 4 sections and put them into one of 4 bins. Okay, and we compute the average score within each of those 4 bins. Now, it might seem basic, but it's true. One of the 4 sections, by definition, would have to have the lowest average midterm score. Right? So if I took the 4 people sitting at the front here, one of you has to be the shortest. Right? Similar idea, if I put everyone in a section, one of the sections has to have a lower average score than the others, unless there are a bunch of ties. Do we agree? Okay. And so it's possible that our section could have just had a low average score due to random chance. Right? It's possible that the section that a student is in makes no difference, and our section just happened to have lower scores on average. Right? But is our section score, so low that it's not explained by random chance, and there are other factors at play? Right? We don't know until we perform a hypothesis test. And so that's exactly what we're going to do. Okay? Any questions with this thought experiment here? Yes, it is. Okay, so here are our null and alternative hypotheses. Okay, the null hypothesis, which again is the one that we will simulate data according to, is that the scores in this section are drawn at random from the scores of everyone in this course across all sections. And the fact that our average score was lower than the overall average score is just due to random chance. Do we agree with this null hypothesis? Right, we can simulate data under the assumption that our section's scores are drawn at random from the whole course's scores. We can do that. The alternative hypothesis is that our section's average score is too low to be explained by randomness alone. Okay, and we can simulate data according to this hypothesis, so it's our null. Yeah? Right. So what you need to think of here is a world in which the section that you're in makes no difference. And so let's just say there are 108 students in our section. I want you to imagine that we just randomly selected 108 of the 393 people in DSC 10 to be in our section. Does our section score look like a random selection of 108 students' scores? That's essentially what I'm asking. Okay, good question. Are we following this example so far? Okay, good. By the way, it was my idea to make this example, not the other instructors. But anyways, so just for some data, our section, like I said, had 108 students take the midterm, and an average midterm score of 46.17. Remember, this is out of 70, right? Not percentage. Okay? And so what this means is, to simulate data, what I'm going to do is ignore section labels for a second and say, okay, let's just pretend we have one really big class with 393 people in it. And what I'm going to do is repeatedly grab 108 random students from the course, not looking at what section they're in, and take their average midterm score. I'm going to do that once, and I'll get one average. I'm going to do it again, I'll get another average. And I do this, say, 1,000 times, I'll get 1,000 averages, okay? Which is the distribution of average midterm section scores under the assumption that our section was drawn at random from everyone in the course. And then we can see where our section's observed average of 46.17 lies in that distribution, okay? So let's see how we would actually do that simulation, okay? Can anyone remember the data frame method for drawing a random sample from a data frame? We talked about it in Wednesday's class. Yeah, dot sample, okay? And what I give it is the number of rows I want to sample from this data frame. In this case, it's 108, because that's how many students are in our section. And now, you'll notice that every time I run this cell, I'll get a new sample of 108 students, some of whom are actually in our section and some of whom are not. Right? But here, we're ignoring the section column entirely. And what I need to do is get the scores and get the average of them. Okay, so every time I run this cell, it's going to draw a new sample of size 108 from everyone in the course and take the average. Okay? And essentially what we're asking is, where does our observed average of 47.16 lie in the distribution of these statistics? And to do that, we have to run this expression many, many times. Normally, we'd like to choose, say, 10,000 repetitions, but since we have a pretty big data set, we're actually just going to use 1,000. In np.arange repetitions, what I'm going to do is say random sample, or like random sample score is whatever this is. I'll keep it there. And I'll say averages equals np.append averages random sample score. So I run this cell, and what it now contains is 1,000 averages. So this is the average of one selection of 108 students from the course. This is the average of another selection of 108 students from the course. So on and so forth. And when we look at the distribution, we see that it looks like this. Okay? So the red distribution is the distribution of average section scores under the assumption that the scores in our section were drawn at random from everyone in the course. Right? So most commonly, if our scores were drawn at random from the entire course, we'd expect the section's midterm average to be somewhere between 47 and 52. Okay, and our observed average was 46.17, which is not really in the middle of this distribution. So there's a question mark, right? Like, which hypothesis does our data better support? And can we somehow make a precise determination on which one it supports? Okay, and so that's what we're going to try and do. So what we are going to do is compute a probability. We are going to compute the probability under the null hypothesis that a randomly selected group of 108 students from the course has an average exam score of whatever our average exam score was, 46.17 or lower. Okay, and that probability that we compute is called a p-value. And so let's just look at it visually. Here, the p-value is the area to the left of this black line. Okay, because, again, this distribution represents the distribution of midterm averages for 108 randomly selected students from the whole course. And this is saying, for instance, the probability that a randomly selected group of 108 students have a average midterm score of greater than 51 is whatever this area is, maybe like 8%. Okay, or the probability that a randomly selected group of 108 students have an average score of 50 or higher is whatever this area is. So starting here, all the way there. That's maybe 30 or 40%. So do we agree with the fact that areas here correspond to probabilities? Okay, so the area to the left of this black line is the probability that a randomly selected group of 108 students has an average midterm score of 46.17 or lower. So we're looking at an area in the tail of this empirical distribution. Here we're looking to the left because low scores point to the alternative hypothesis, which is that our score is lower than one would expect. Do we agree? So we're looking to the left here. And this area on the left is our p-value. Okay, so let's actually compute it. Our observed average, again, was 46.17. And the results of our simulations come from this array averages. So what I want to do is figure out what this area to the left of the black line is, or in other words, what proportion of our simulated test statistics were less than this observed average. And so how I can do that is by comparing this array averages to observed average. So the first simulation, its observed average was greater than 46.17. So was the second, so was the third, so on and so forth. And to figure out what proportion of these are true, I can sum them up or use np.count non-zero. So this will tell me one of my 1,000 randomly selected sections had an average less than or equal to ours. And so as a proportion, I'll use repetitions here, that is 0.001. Okay, so what this is telling us is that the probability that a randomly selected section of size 108 from everyone in the course has an average lower or equal to our section's average, that probability is 0.001, or 0.1%. Do we agree? Okay, so this is the p-value of this hypothesis test. Okay, and so more specifically, or more generally, I should say, the p-value is the probability under the assumption that the null hypothesis is true, that the test statistic is equal to the one we observed, or more extreme in the direction of the alternative hypothesis. Right? And so this is why it's important to design your test statistic correctly, right? So it's clear what we mean by direction of the alternative hypothesis. In our case here, the alternative hypothesis was that our scores were lower than one would expect, and so we look to our observed statistic, 46.17, and to the left, because left is lower. Do we agree? Okay. Another piece of terminology to be aware of, sometimes this comes up in assignments, is observed significance level. That's just a fancy term for the p-value. Okay? Now, this is kind of reiterating what I just said. In our example, we looked at the area to the left of the black line, right? To the left of the observed statistic. Sometimes we will look at the area to the right of the observed statistic. And in our final example today, we will do just that. Okay, so what do we do with this p-value? Well, the whole reason we went on this exploration was to pick which of two hypotheses our data better supported. Okay, and how can we interpret this p-value? Now, the p-value is not the probability that the null hypothesis is true. Right? That's an incorrect interpretation of the p-value. What the p-value is the probability that under the assumption the null hypothesis is true, a random section has an observed average equal to ours or lower. That's what the p-value is. Okay, it's not the probability that the null hypothesis is true. Okay, but anyways, if the p-value is sufficiently large, if it's above some cutoff, well then it doesn't seem all that much of a stretch, that the null hypothesis is true, right? For instance, if we go back here, and this black line was, say, at 48, and our p-value was like, 15%, it wouldn't seem all that unlikely that our section's average did come from this distribution. Do we agree? Right, so if this line was somewhere over here, and the area was much greater, then it seems like our data, our observed data, is consistent with the null. Do we agree? Okay. But if the p-value is below some cutoff, well then it seems like our observed data is inconsistent with the null hypothesis, And based off of whether it's consistent with the null or inconsistent with the null, we either fail to reject the null hypothesis or reject the null hypothesis. Okay? So if the data are consistent with the null, we fail to reject it. We don't accept the null hypothesis. Okay, I'll tell you right now, this will probably be a trick question at some point. Can we say we accept the null? Right? We don't accept anything because we truly don't know how the universe works. Right? All we have access to is data in a sample, and there are a variety of reasons for why the data looks like it did. Right? So it's kind of semantic, but we always say we failed to reject the null rather than accept the null. Because there are other possible reasons other than the null hypothesis for why the data looked as it did. Now, again, if the p-value is sufficiently small, if it's below some cutoff, we say our data are inconsistent with the null, and we reject the null hypothesis. Okay, so if the p-value is low, we reject the null hypothesis. Now, what do we mean by a low p-value? Okay? Now, the answer is that it's kind of subjective. And truly, some statisticians, like 100 years ago, came up with commonly accepted cutoffs, and kind of arbitrarily, we still use those cutoffs today. So for instance, a common p-value cutoff is 5%, or 0.05, but there's really no rhyme or reason for why it's 0.05. We just happen to use it because it's been used for 100 years. Okay, but that's like the most common cutoff. If the p-value is below 5%, below 0.05, then we reject the null hypothesis. Otherwise, we typically fail to reject it. Okay? It's not the only cutoff we could use. We could also use a cutoff of 0.01%, which means that the bar for rejecting the null hypothesis is much higher. And there are some qualitative terms associated with these cutoffs, like statistically significant or highly statistically significant. But what I'll say is that these cutoffs are arbitrary. We will follow them because it's typically what folks in statistics do. But I wouldn't blame you for questioning why are we picking 0.05. That's kind of just the way it is. Do we agree? Okay. So what does this mean again in context? Well, here's another way to look at it. The p-value cutoff that we choose, say 5%, is an error probability. And here's what I mean. Suppose we choose a cutoff of 5%, which might correspond to, say, an average exam score of 47 or something. Or pretend that's our cutoff. Under the null hypothesis, it is possible to see a random section whose average score is lower than 5%, or sorry, lower than 47. Right? We did see that in our simulations. Not often, only 5% of the time, but we did see that. And so if you choose a 5% cutoff, then roughly 5% of the time, when you run hypothesis tests, you will incorrectly reject your null hypothesis. Right? Because if our cutoff is here, and our observed statistic is here, we might reject the null, even though the data were consistent with the null. Right? So these cutoffs, they're not totally scientific. Right? When you make a determination using a hypothesis test, it's not a guarantee that the hypothesis you sided with is true. Right? It's just what seems more likely given our data. Do we agree? Okay, questions with this example so far? Questions with the example? Yeah. The probability that under the null hypothesis, or the probability of, under the null hypothesis, seeing a test statistic equal to the observed one or more extreme in the direction of the alternative hypothesis. Yeah. Cool. So, before we move forward, let's theorize. Like, why did our section have an average, a lower average? What do you think? Well, here's one answer. Teacher, I'm not going to say that, sucks. What are the other options? The what? Yeah, the time. That's what I actually think the answer is, the time. 1 p.m. Right, and the reason I think that's the option is when I taught this last fall and taught at 9 a.m., my section's average was equal to or higher than all the others. So I'm pretty sure it is the time. But other options, yeah. The location, yeah, that's big. Any others? Yeah. That's possible. It's not actually true. Like, attendance is low in all sections, but yeah. Anything else? Yeah. Well, I'm not going to say that. Here's another possibility. I'm going to just write it. This is a possibility also. Anything else? Okay. Here's how I look at it. We have the lowest average score, which means we have the most left to learn. Okay? Okay. Anyways, enough of that example. Our final example of the day will be more similar to something we looked at on Wednesday, okay, which involved jury panels and how jury panels are drawn from eligible populations. The first example we looked at involved Robert Swain in Talladega County, Alabama in 1965. This example is a bit more recent. It involves Alameda County in a study that was performed between 2009 and 10. Who's from Alameda County? There have to be a few people, right? Okay. Anyways, so as a reminder, from lecture 15, the way that jury panels are drawn are, in theory, as random samples from the eligible population. So once again, we are looking at this step. We have an eligible population, and the jury panels should be random samples from this eligible population. And then who actually ends up on the jury, well, that's determined not randomly. That's determined by interviews by the judges and the lawyers. But we're looking at this first step. Okay? And just for some added context, since we're looking at Alameda County, which is in Northern California, if you're not familiar, the California's Code of Civil Procedure says that all persons selected for jury service shall be selected at random, yada, yada, yada. The point is, it's not just like an idea in theory that jury panels should be selected at random. It's like the law. Okay? And so the data we're looking at, again, comes from Alameda County between 2009 and 10. And the study looked at 1,453 people who reported for jury duty, so who showed up in jury panels. And from now on, we will call them panelists. Okay, and so what we're going to look at here are two distributions. One is the distribution of the eligible population. So this is the population of Alameda County. Okay, and the second distribution is the distribution of those who showed up on jury panels. Okay, and one distribution is supposed to be constituted of a random sample from the other distribution. That is, the panelists should be a random sample from the eligible population. But what do you notice here? Yeah, they're different, right? They're not different in all categories. For instance, the white proportion is the same in both distributions, but some are quite different. For instance, the Asian proportions are quite different in the two distributions, as are the black and as are the other Latino. Okay, so the jury panelists are supposed to be drawn at random from the eligible population, but here are the distributions we ended up with, right? And so, again, we want to test this hypothesis, where specifically our hypotheses are A, the null hypothesis, panelists were selected at random from the eligible population, and the alternative hypothesis, panelists were not selected at random from the eligible population. Okay? Those are our hypotheses. We have our real-life observation. We have the distribution of those 1,453 panelists who actually showed up to serve on a jury. But the question is, it's not clear what our test statistics should be, right? Because all of the test statistics we've looked at so far typically involve like the difference in counts or the difference in proportions. But those only worked when we only had two categories, like heads or tails. Right? The most recent example where we looked at midterm average scores, that didn't involve categorical distribution, so it's not quite the same. But here we have two categorical distributions, each of which have 5 categories. And we need a way of summarizing how different these two distributions are using just a single number. Do we agree? right? Somehow we need to condense the differences we see, right? This difference, this difference, this difference, this difference. We need to summarize all of that with just one number. But we haven't done that yet. Do we see the problem? Okay, so somehow we need to quantify this. Okay? And so here's how we're going to go about it. First, I'm going to take these two distributions, and I'm going to subtract one from the other. So I'm going to subtract the panels column by the eligible column. So you can see the white proportion was 0.11 higher for the panelists than in the eligible population. And the black proportion was 0.1 lower than it was in the eligible population, and so on and so forth. So do we see where this difference column came from? It's quantifying how different each individual category is. But what we're looking for is like a single number that summarizes how different these two categories are, or sorry, these two categorical distributions are. And it's a mathematical fact that if I just add up the difference column, the result is going to be 0. We're not going to look at why that's the case. That's something you'll study in courses like DSC 40A. But if you add up this difference column, the result is 0. So to avoid that cancellation, all I'm going to do is take the absolute value of the difference column. Okay, and so now none of the entries here are negative, and I can add them up and get something that's non-zero. Do we agree? Okay. So if I add these all up, that is, if I add the absolute difference column up, that'll give me some estimate of, or some measure of how different the two categorical distributions are. Again, to be precise, this column, that's one categorical distribution. This column, that's another. So this column kind of explains how different the individual proportions are. And if I want to, combine all of these differences into a single number, what I can do is just add up these absolute differences. And that's almost what the total variation distance does. So the total variation distance is a new test statistic, and it only has one purpose. It measures how different two categorical distributions are. It measures how far apart they are. And it is computed by taking the sum of the absolute difference in proportions and dividing that all by 2. Okay? We divide by 2 instead of just adding them, so that, for instance, the distribution 0.51, 0.49, its distance from 50-50 is only 0.01 instead of 0.02. Okay, and in the next class, we will further interpret, what exactly the TVD means. But here's the TVD between these two categorical distributions, 0.14. Eligible and panels, this number, 0.14, describes how different they are. Do we agree? Okay. Pardon? Yeah, this is a single number. This is not tied to any one category. It describes how different these two columns are. Okay, it's the TVD, and there's a divided by 2 in it. And we'll revisit the TVD in just a sec, but all I want to do here is show you that it's, I should really quickly implement this, return. Really quickly, we'll, oops, did I do this correctly? No. The end result is nothing but a simulation like the ones we ran before. Okay, all that's new here is how we computed the values on the x-axis, how we computed the statistic. These statistics now are the TVD, and the result we interpret the same way as we did before. Here, clearly, this observed TVD is way out of this distribution, and so it seems like our observed data sides with the alternative hypothesis. Okay, we will review the TVD when we come back on Wednesday.